and subtracting rational expressions. So rational expressions, even with variables, act just like regular fractions. In order to add or subtract, you have to have a common denominator. So with these, we multiply what I like to call a fancy form of 1. Because if you multiply something by 1, you're not changing anything. For example, if I multiply something by 8 over 8, I'm really just multiplying by 1, so my problem's not really becoming different. If I multiply by something by, let's say, 2 over 3, well, that's not equal to 1. So if I take 4 and multiply it by 2 over 3, I'm actually now having 8 over 3. If I take 4 and multiply it by 8 over 8, well, that's really just doing 4 times 1, and I'm still getting a 4, it just looks a lot bigger. Now it would be 32 over 8 instead, but that still simplifies back down to a 4. So you can also make fancy forms of 1 with multiple terms. For example, 7x plus 2 over 7x plus 2. Since it's the same thing over itself, that's still a 1. So your 1s may not look quite as simple as we're used to, but something divided by itself is still equal to 1. So example 1 and 2 are the basic kind. If you have, for example, 5 over 21x plus 2 over 21x, well, those denominators are already the same. So we simply add the numerators. We get 5 plus 2, and we're adding because of the plus in the middle, and the 21x stays in the denominator. We don't change a denominator when you add. Even if we did 1/3 plus 5/3, that would still be 6/3. The 3 in the denominator doesn't change. Now 5 plus 2 does make 7, and I can actually simplify 7 over 21, which makes 1/3, so I get 1 over 3x as my final simplified answer. Subtraction works very similar. Again, the denominators have to be the same. In this case, they are, so we can go ahead and subtract the numerators. So 4x minus 3 over x minus 5, because again, the denominator does not change. Now here, we can't really simplify this any further because there are no factors that are the same. Yes, there's an x and an x, but those are terms, not factors. Factors is if they are multiplied into something. That is where we can actually simplify things down. So this is as simplified as this one is going to get. Let's look at rational expressions with unlike denominators. So this is mainly what you're going to be seeing. So here are your 4 general steps. Step 1 is to factor the denominators. This way we can see exactly which pieces should be included to create common denominators. So for example 3, here on the right, we have x squared minus x minus 12 in the denominator. So I know that this is something that I can factor. So I'm going to do that over here on the side. So x squared minus x minus 12. So because the a value is 1, we can do our shortcut. We need 2 numbers that multiply to be negative 12, but add up to be negative 1. So the 2 numbers that do that are negative 4 times 3. So those are our factors, x minus 4 times x plus 3. So my new expression becomes x over the factored version, which is x minus 4 times x plus 3. Then we have a plus 5 over, and if I look at this denominator, x minus 4, well, that cannot be factored any further. So we're just going to leave x minus 4 the way it is. So now that we have all the factors, or all the denominators factored, step 2, determine which factors are needed in which fractions to make the denominators common. So if I look at this first fraction, I have x minus 4 and x plus 3 in my denominator. On this fraction, all I have is the x minus 4. So this one is missing x plus 3. That's where the fancy form of 1 comes in. So we're going to multiply this second fraction by x plus 3 over itself. Because remember, if I multiply by 1, nothing really changes. It's going to look different, but something times 1 is still 5 over x minus 4 in reality. So your first fraction is not going to change. That has exactly everything we need. X minus 4 times x plus 3. The second fraction, however, will be multiplied by x plus 3. So if we do 5 times x minus 3, I'm going to write it this way first. 5 times x plus 3 over x minus 4, which is really in an invisible set of parentheses because they are 2 terms. They're locked together. X minus 4 times x plus 3. So if you notice, this is something that we could technically simplify. X plus 3 divided by itself, we can simplify that out because it's a 1. However, if we do that, we end up back where we started, which isn't helpful. We're trying to combine these together. So if I look at the denominators now, we have x minus 4 and x plus 3, x minus 4 and x plus 3. So these denominators are now the same. Since they're the same, I can now add their numerators. So I can take x plus 5 times x plus 3 in the numerator, and then the denominator will stay exactly the same as x minus 4 times x plus 3. Now remember, we cannot simplify this here because we added these fractions together. This is no longer a factor. This is part of this single term here, so I cannot simplify those out. What we can do, however, is multiply this in. So we have x plus 5 times x is 5x, 5 times 3 is 15, all over x minus 4 times x plus 3. We're trying to get this as simple as we can here. I can combine like terms in the numerator. So we get x plus 5x, which makes 6x. I'll go to the side. 6x plus 15. And again, the denominator just kind of tags along through this entire process. Now, let's see if I can factor this out and maybe cancel out or simplify out one of the denominator factors. I can divide 6x and 15 both by 3. And we end up with 2x plus 5 left over x minus 4 times x plus 3. So even with factoring the numerator, we still did not end up with something that could simplify one of the factors in the denominator. So this is as simple as this fraction, this rational expression, is going to become. So that's adding two fractions together. Let's look at how we add 3 on example 5. And then you guys are going to do example 4 by yourself. So we're going a little bit out of order here, but that's okay. So example 5, we have x plus 2 over x minus 4 plus 2 over x minus 5x over x squared minus 4x. Well, again, make sure everything is factored out as possible in the denominators, because remember, your goal is to get the common denominators. That is your goal. We want common denominators. That's the goal. So here, x minus 4 is fully factored. X is fully factored. So this third one, we can actually simplify that out a little bit. So x squared minus 4x, I can factor out an x, and we're just left with x minus 4. So let's rewrite what we have. The first fraction, we weren't able to factor the denominator, so nothing changed. Plus, the same thing with the second fraction, stayed the same, minus 5x over, but the third fraction, we simplified that denominator into x times x minus 4. We factored out that denominator. So now that all of the denominators are in their factored form, let's look and see which factors are missing in which fractions. So I always like to start with the fraction that has the most factors in its denominator, which in this case is our last one. This guy has an x and x minus 4. So I need to make sure the other two fractions have both of these things. And if I have something in the other fractions that this one's missing, I'll need to multiply that to this guy as well. So this one has an x, and so does this. So I see that this second fraction will need an x minus 4. He has the x part, just not the x minus 4. This first fraction has x minus 4, but he's missing the x. And so this first fraction will need x, and that's going to be in parentheses. So now that we have determined exactly what we're missing and what we need, let's multiply by our fancy forms of 1. So this first fraction, x plus 2 over x minus 4, will need to be multiplied by what the factor is missing. In this case, x over x. Then we're going to add 2 over x, and the second fraction needs to be multiplied by the missing factor of x minus 4 over x minus 4. Now the third fraction wasn't missing anything. It had exactly what the other two did. So that third fraction will not need to be multiplied by anything because he already has all of the factors these other two did. Now let's go through it and multiply out. And again, I'm going to write it without multiplying first. So we're going to do x plus 2 times an x. But since x is just a single term, I'm going to put the x in the front. So it's x times x plus 2 over Then we're going to still multiply x, because it's a single term, I'm going to leave it in the front, times x minus 4. So that is our new first fraction. Plus, we have 2 times x minus 4 over, and then again, x times what we're multiplying is x minus 4. And again, we don't want to simplify, because if we simplify, we end up back where we started. And the third fraction stays exactly the same. Now look and see here, x minus 4, x minus 4, x minus 4. So all of these denominators are now the same, which means we can simply add together all of their numerators. So we're going to have x times x, which makes x squared, x times 2, which makes 2x, plus, because there's a plus here, 2 times x, which makes 2x, and 2 times negative 4, which makes negative 8. Now, when you do a minus a number, make sure when you do minuses, you put it in parentheses. And the reason is just in case there's more than one term. In this case, it doesn't really do much of a difference because a negative times a 5x is still negative 5x. But if there had been 2 terms, it would have changed your solution. And all of this is over the single denominator of x times x minus 4. Finally, let's combine any like terms that we can. So x squared does not have a like term, but I can combine 2x, 2x, and negative 5x. So negative 5 plus 2 results in a negative x. And negative 8 does not have a like term. And still, we are still over x times x minus 4. Last but not least, let's look at our new numerator and see if we can factor this out. So the idea is we want to see, is there a number that multiplies to negative 8 but adds to be negative 1? Well, negative 1 times 8, if I add those, I get, sorry, not 9, I get 7. That's not right. Negative 2 times 4, if I add those, I get 2. And then there's no other factors of 8. So this isn't something that's going to work. So that means the numerator does not factor. So this is as simple as this rational expression will become. So pause the video, try example 4. So here's what you should have had for the multiplication. This is the factored form of the new denominator. This first fraction is missing the factor of 2. It has the x minus 2 part. Now the next step would be, now that these are the same, we need to subtract the numerators. But remember, when you subtract, we need to be careful with multiple terms. So the 4x will be subtracted by 5x minus 1. So since there is more than one term in that second numerator, we need to make sure we keep parentheses, because we really have to take this negative 1 and distribute it out. And so what we really have is 4x minus 5x plus 1 over 2 times x minus 2. So be careful when you are subtracting multiple terms. So let's continue. Combine what we can. 4x minus 5x is negative x plus 1 over 2 times x minus 2. And this guy will not factor. We can divide out a negative 1, but even if we divide by negative 1, we still don't get one of the factors in the denominator. So this is as simple as this rational function will become. The next part is looking at complex fractions. So a complex fraction is basically a fraction in a fraction. So lots of fractions going on here. Break this into essentially 3 parts. The first thing we want to do is simplify the numerator. As far as we can, simplify numerator and of the big fraction. So really we have a little fraction inside of a little fraction. So we've got 2 fractions going on. So we're going to simplify just 6 over x minus 2. However, 6 over x minus 2 is already simplified. I can't really make it go any easier than that. Step 2 then is look at the denominator. See if you can maybe simplify that. So simplify the denominator. So my denominator is 1 over x minus 2 plus 3 over x. That is something that I can simplify. And so we're going to add these 2 fractions together. So pause the video. I want you to add these 2 fractions together, unpause, and we will continue with simplifying this complex fraction. Okay. And here's the simplified version of that denominator here. So now step 3 is let's put everything back together. So step 3 is we're going to put everything back together. Put back together. So our numerator didn't change. That 6 over x minus 2 was as simple as we could get it. So 6 over x minus 2 all over the denominator, however, simplified into that red fraction. 2 times 2x minus 3 over x times x minus 2. Now, when you put it back together, we want to actually divide these fractions out because that's what a fraction in a fraction is. This is saying 6 over x minus 2 divided by all of this fraction on the bottom. So remember, when we divide fractions, we keep the first fraction, so in this case, the top, change to multiplication, then flip the second fraction, which in this case is the bottom. So what this turns into is we're going to keep 6 over x minus 2 times, change that big division sign into a little multiplication sign, and then we flip the denominator. So in this case, this x minus x times x minus 2 will now be in the numerator, over this is now in the denominator, 2 times 2x minus 3. Because now that we are here, I can see that when I multiply fractions, remember, we can simplify common factors across the entire expression. So I see that x minus 2 and x minus 2 are the same factor, so we can actually simplify that out. And what we're left with is 6 times x, which is just 6x, over, and this is really a 1 times 2 is 2 times 2x minus 3. One last thing is I see that 6 and 2 are both factors because 6 is being multiplied to x and 2 is being multiplied to 2x minus 3. So I can simplify 6 divided by 2. Well, 6 divided by 2 is a 3x over 2x minus 3. So complex fractions can be easily simplified if you break it down in pieces. So your basic 3 steps are simplify the numerator, simplify the denominator, put it all back together, and divide, which basically means multiply. So I would like you to pause this video and try example 6. And here would be your solution for example 6. Let's look at a real-world application. So it says the total resistance RT of two resistors in a parallel circuit with resistance R1 and R2 in ohms is given by the equation shown. Simplify the complex fraction, then find the total resistance when R1 equals 2000 ohms and R2 equals 5600 ohms. So this is an equation that is mainly used with circuitry and electronics and electricity and all those things. Ohms is the unit for what we call resistors. So we need to find the total resistance of this given circuit. And so this is the formula that is used. Now, there's a couple ways you can start this. You can either simplify the complex fraction first, this guy here, just like we did in the above two examples, or I have to the values of R1 and R2. I know what both of these numbers should be. So we can also substitute both of these numbers into R1 and R2 and then simplify to find the total resistance. That's what we're looking for. I'm a fan of option number 2. So I'm going to plug in the numbers that I have. So let's see. R1 is 2000 and R2 is 5600. Let me write that over here. So R1 is 2000 and R2 is 5600. So let's plug that in. So the RT, which is the total resistance, is equal to 1 over R1, which is 2000, plus 1 over R2, which is 5600. So we can't do the division yet. So we can't do the keep, change, flip yet because we have two fractions added together in the denominator. I can only use keep, change, flip when it's a single fraction over a single fraction. So first we need to add these two fractions together. But now there aren't variables, so we're going to do this just like we did back in earlier grades. So we need to, so let's see, RT equals, we're going to keep dragging that down. RT equals 1 over, okay, so 1 over 2,000 needs 5,600 multiplied to it. 5,600. And then plus 1 over 5,600 needs that 2,000 multiplied to it. So 2,000 over 2,000. So we're going to get some pretty big numbers here. So now we have, let's see, RT is equal to 1 over, so this is 5,600 over, and I'm going to leave this just in its multiplied version just for a minute. Because if you actually multiply 5,600 times 2,000, you get a pretty big number. So I'm just going to leave it multiplied for now. 1 times 2,000 is 2,000, and again, I'm just going to leave it multiplied as 5,600 times 2,000. Now that the denominators are the same, I'm going to move my work up here. RT equals 1 over, notice how we're only working in the denominator. We're not working with the top yet. Now that the denominators are the same, I can go ahead and add this plus this. So 5,600 plus 2,000 is equal to 7,600. So we have 7,600 over, and I'm going to go ahead and multiply 2,000 times 5,600, which gives us 11,200,000. So lots of zeros. We have successfully combined the two denominator fractions. So now I have a fraction over a fraction. Remember, I can rewrite 1 as 1 over 1. So now we can divide these two fractions out. So when we divide two fractions, we keep the first one, change division to multiplication, and flip the second one. So 11,200,000 on the top over 7,600 on the bottom. Now, 1 times this other fraction is still just this gigantic number. So I'm going to go ahead and start simplifying this guy. So I know that these zeros will divide out. That's a factor of 10. These second zeros will divide out. That's a factor of 100. So RT is equal to 11,200 and an extra 0. So what is that? 112,000 over 76. Now we can simplify this fraction further. I know that I can divide both of those by 2 because both of them are even. So 112,000 divided by 2 will give us 56,000 over, and if I do 76 divided by 2, we get 38. And since they're still even, I can still simplify. So we're just going to simplify as far down as we can. 56,000 divided by 2, we get 28,000. And that's about as far as we can go because 28,000 is not divisible evenly by 19. So we can either leave it as the resistance total is 28,000 over 19 ohms, or you can write it as a decimal. 28,000 divided by 19 is 9.5. 9.5 ohms. Or you can write it as a decimal, which is 1,473.68, that's rounded, ohms. So either way, either if you simplify the complex fraction first, or if you plug in your numbers and then simplify, either method will get you to the same answer of a total resistance of 1,473.68 ohms.